Hi, Phil Whitehead back again for video number 2. In this, I'm going to take you through a series of notional or fictitious business processes and what to look for in those and how to go about studying these. And we're going to use a term called modeling, and we're going to use that term in several more videos, but I just want to introduce you to the concept of modeling at this point, and that's a way to observe complex systems by using a representation of those systems. And so that's what I'm going to use in these simple models. And the objective of these models is just to teach you some of the concepts of synchronous flow. While I'm going to use manufacturing as the model, so to speak, that's not necessarily constrained to manufacturing. We've used successfully these models or these techniques in dentist offices, doctors, lawyers, etc. Anything that has a business process and a determined end to that process. Thanks a lot. Let's go.
Okay, let's jump into our notional models study, and the purpose of this, once again, is to facilitate your learning, not to represent real-world systems so much. In this model, as we chatted about a few minutes ago, I'm actually going to use a manufacturing system as it's easier for most people to understand. Although I want to add this word of caution is that this modeling techniques or this approach works for all types of businesses, from emergency rooms to doctor's offices to lawyer practices to about anything that you can think of that has a business process or a system, as we defined in the first video. And in this system that we're going to study today, we're going to have an order management process that receives orders from customers and forwards them to manufacturing. We're going to have a manufacturing process that makes the product for the customers. We're going to have a delivery process that packs and ships it to the customers, and that's what we're going to study. We'll add a little twist a little bit later in the video. What is an effective system? Well, in an ideal world, all the orders are received by order management. They're manufactured without delay, and they're delivered to the customer on time. That's the ideal world. And that's our objective. So in this demonstration of an effective system, we have 3 types of demand. We have customers, forecast, enter plant, and those all feed into an order management system that enter the order. These are processed, and it takes time and resources to process those. They're handed off electronically to the manufacturing process. They do all the planning and scheduling and supply chain management and etc. Once it's manufactured, it's delivered either to finished goods inventory or to the shipping or department for delivery. And again, resources are applied as I have to box these up perhaps, and finally deliver those to my customer. So that's our simple process that we're going to study, and let's dive right in and see what can happen to us in some real-world scenarios actually. So order management and delivery are efficient, product is delivered on time, the system works. So all is good, all is well. So potential problem number 1, manufacturing produces all the orders processed by order management, but delivery cannot handle all of them. Well, what can happen? Well, before we get into that, let's look at order management. You see my resource utilization here in this yellow sliver. We're considering 100% utilization, as in reality about 85%, because you do have safety meetings, you do have bathroom breaks and etc. during the course of the day. So any system that is at 100% resource utilization through time becomes an inefficient system, and that's an important point that you might want to take note of. The orders come into manufacturing and they make them. Resource utilization was dead on, let's say at about 85%, and then everything's looking pretty good, but I get to delivery and the resource utilization is pegged. I have no more resources to process the orders. And so delivery is overutilized and inventory increases. Well, why did inventory increase? Well, because manufacturing kept making at the rate that orders were coming in from the customer. And the delivery system could not ship them fast enough to the customer to meet the delivery expectations. So what happens is we build a queue or inventory. We also have inefficiency in our delivery process, and sometimes that can be compensated, at least on the very, very short term, with overtime. But in the long haul, we just have to balance out the resources, or another possible alternative is slow demand down. Normally not something that you want to do, but it is an option. So delivery is overutilized, inventory increases, and the product is not delivered on time, therefore the system fails. Does that make sense to you? Potential problem number 2. Order management receives and processes more orders than manufacturing can produce. Well, we didn't have a problem in order management, so everything's just chugging along just fine. No problem. Order management is efficient. However, we are overutilized and the orders build in queue in manufacturing. So, okay, maybe I can work some overtime, blah, 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 but what's the effect on my total system? Well, delivery becomes underutilized, and just as importantly, the product isn't delivered on time, therefore my system fails. Does that make sense? Do you see the relationship between the arrows in the different business processes there? That's the key to understanding change management and process improvement. So many people make changes to their system without understanding these relationships, and they make a change, let's say in manufacturing, to improve the efficiency, only to see a problem pop up in delivery, in this case, because I'm overutilized in delivery. I did not plan for that added surge of inventory coming into me. So hopefully that makes sense to you. Next, let's take a look at the case when manufacturing has 2 steps. So order management receives more orders than the second manufacturing step can produce. So it looks something like this. Order management's fine. Operation number 1 is fine. Everything's looking good. I get to operation number 2 within manufacturing. It's overutilized, and work in process builds in queue, meaning delay. So queue means delay, not unlike your other grocery store, and you're waiting in line to check out. Same thing happens in your business processes. Now think about that in your own business. Have you ever seen that happen? So I'm sure you have. And so what we want to do when we're considering total systems is solve for that before it occurs if we're contemplating change. So work in process builds. The delivery is underutilized once again. The product is not delivered on the time. We've got unhappy customers, and the system fails. Make sense? So now let's look at a synchronous flow. Is a smooth and continuous movement of entities through the entire total system. The characteristics include minimal delays, reduced cycle times, reduced inventory, and the like, and lower operating expense. So if I have a demand for 2,000 widgets in a week processed through order entry, and I get those through order entry, the order completes all the orders with a 90% utilization, so life is good. Order management is not a constraint. Now, order management sends the requirements of the 2,000 widgets to manufacturing per week. I'm adding the dimension of time here a little bit. Manufacturing produces all the widgets required, but they were 100% utilized. Now what does that mean? It means that I satisfied the demand at least in the short term, and I was able to produce the 2,000 widgets by working overtime, perhaps hiring temps. Manufacturing is now a bottleneck. And the concept of bottlenecks is they must be managed. And now we're into the theory of constraints. When you have a bottleneck, and it is a long-term or a system bottleneck, then we have to do something about that bottleneck, and that's pace the rest of the organization to that bottleneck, unless the bottleneck can be changed or moved. But you don't remove a bottleneck unless you can predict what's going to happen downstream from that bottleneck. Very important concept. And it goes back to the problem where you fix one thing, like a tube of toothpaste, you squeeze it, and the problem, I'll be doggone if the problem doesn't pop up elsewhere. So we want to avoid those things. That's inefficient change management when we do those things. And oh, by the way, I see that time and time again in the real world. So back to our example. Overtime is added, makes the operation efficient. Delivery can only ship out 1,800 per week with 100% utilization. So now delivery becomes the bottleneck. Oh my goodness, I just squeezed the tube of toothpaste and look where it popped up. Isn't this fun? And by the way, folks, I am leading toward a solution in a couple more videos that I'm going to talk about to be able to study and predict this with pretty good high degree of certainty. Inventory is building between make and delivery, and shipments are delayed, therefore my system fails. So a synchronized solution would look like this. Sufficient resources are added to delivery so that it can produce the 2,000 widgets per week with a 90% utilization. On-time delivery moves to near 100%, and the system is synchronized with current demands, and we have happy customers. So that's the concepts that we're teaching here. I want you to go back and think about those and consider them in your own business, because we're going to go through and add some complexity to this layer, and we're going to give you some techniques by which you can study these systems, which are far more complex than what I just went through in this little conceptual demo. However, we would appreciate your likes on YouTube if you like what we're doing. But especially your comments, because this will help us guide us as we read your comments into deeper dives, perhaps, or more complex business models, or an example in your particular industry. Just whatever your thoughts are, or if you hate it, I mean, that's fine too. Your feedback is always appreciated. Thanks so much.